So, in the previous lecture, that is lecture 15, we have started discussing about queuing theory. So, we have started understanding in a particular queue or in a queuing system, what are the things that are there. So, that is something we have discussed, and then we have also started discussing how a queue interact with the other events which are external to the queue, but which actually influence the queue, such as the arrival or the duration of the call or duration of the whatever service you are giving. So, those things, and we have also started discussing about from there how do you get a feel of the associated random process that goes through the queue. So, this is something we have started discussing. Okay. So, basically what today we will try to do, so we have already identified that there is two things which are important in queuing, so which are external to the queue, which is arrival and service process. So, today we will try to characterize some of the very well known arrival and service process with their very remarked properties, which has been used in deriving mathematical tools for queuing. And you will see that it is not only just it is a mathematical beauty. So, it has a huge application, because all the telephony networks that we have been discussing, like trunk call and all trunk switch analysis we are trying to do. So, there it has been seen that the arrival process actually follows that the one I will be talking about, which is the Poisson process, and the service process also what we will be talking about, the exponential service process. So, these things actually it has been measured and it has been observed over the years that these things follows those kind of distribution. So, it is not that it is just a mathematical thing that we will be discussing. These have huge practical application, and most of the trunk switches till these days also are designed by the principle of the formula or theory that we will be developing now. Okay. So, basically we have given some introduction. As you can see, now we will start discussing about the arrival and service process. Okay. So, it is popularly known as Markovian queues, and we will see with single server, multiple server, that is something we will see later on. But we have also started discussing about a typical queuing system where you have queue and server, and then we have started discussing the timeline, that how customers arrive, how they interact with the queues, and what kind of series of events that occurs, and what are the associated randomness that are involved in this process. And then try to see what are the basic things we can talk about this arrival process. Okay. So, that will be the most important part that we will be discussing in the beginning. Okay. So, let us try to see, we are trying to discuss about a process called arrival process is nothing but in time, if you see. So, in the timeline, so it is actually either packet or customer or call, whatever it is, they in time frame they do arrival, and generally they are random, because each customer is making arrival to the queue. Of course, it is to a particular service center, switching center or queue. So, it is a random arrival that will be happening, and this is actually the account of these random arrival with their timestamps. Okay. So, this is actually described by a it is actually a time series. That means different time instances where particular arrivals, arrival number 1, arrival number 2, 3 and so on has happened. So, it is an account of these things or bookkeeping of these things. Okay. That is actually arrival, and because it as you can see it is random. So, it varies with time, it does not really, the pattern does not really repeat. So, it varies with time in a random fashion. So, it is a associated random process, okay, or it is described by a associated random process. So, what we will try to do, we will try to characterize if we can really describe about the associated randomness, okay, and that random process if you can characterize through some mathematical description. But before describing the randomness, you all know a little bit about random process. So, here we will give a very brief introduction to the random process that we are talking about. So, over here the random process will be actually a stationary random process. Okay. So, what do we mean by stationary random process? That means whatever statistical description we will be giving, that statistical description does not really change with time. So, that means if you take all the statistical property, let us say you take the average, you take the second moment, or you from second moment you derive the standard deviation. So, these things does not change over time. So, at whichever time, suppose for a queue, particular queue there are arrivals, or let us say for a trunk switch there are customers who are arriving. Now, this customer arrival process does not change, or the statistical property of that process does not change with time. That means, if you take a certain time window, let us say 1 second or let us say 1 hour. So, 1 hour in one day if you take and then try to evaluate how many customers are arriving at that 1 hour, and then if you keep on moving and then try to see the average value of it, it will not be actually, if you take average over ensemble, it will not be really changing over time. Let us try to understand this ensemble average little bit. So, there are two kinds of average that can happen. So, let us say I have a time window where different kind of arrivals are happening. So, whatever it is. Now, suppose I have fixed a time window called T. Okay. Over this T, I will be taking multiple samples, and the way we derive the statistical properties is we take average, means we take actually in multiple windows we take samples, and over that we infer the statistical property. So, if we wish to take average, we take multiple such instances T windows or window of T length, we calculate or count how many arrivals are happening. So, that is probably we will be counting, and then we will try to see what is the average number of count that are happening. Okay. Now, this averaging we can also do in two different ways. Let us try to understand what are these two different ways. That will give you a basic understanding of random process. So, even though you have been taught random process probably in your earlier courses, but I will still give a brief idea about it. Okay. So, what will be happening over here, as you can see, if we just keep on observing, we can observe over multiple time instances. Okay. So, basically you have recorded this particular arrival for a very long duration of time, and then for different T over the time for the same that arrival history that you have recorded, if you take and then do an average over all these time windows. So, basically you keep on doing that, and then you take an average over all these windows and then try to give over T time how many arrivals are happening, or from there we can divide this by T. So, per unit time how many arrivals are happening, or it is called the arrival rate. So, number of arrival per unit time. Okay. So, basically you will be evaluating the count. So, count you will be getting everywhere, and then those count you will average over the number of instances, and then you divide by T. So, that per unit time number of arrival you will be getting. So, this is actually a very important parameter which is called lambda. Now, all we have to see is whether this average is the average we are talking about. So, this is one average of course, but this is called the time average. What are the other average that is there? The other average is called the ensemble average. What do I mean by this ensemble average? So, ensemble average is something like this. So, you actually prepare this kind of queue, identical queue, multiple such queue, infinite number of queues. So, basically you will be preparing all identical queue for which you know identical kind of arrivals are happening. Okay. So, say with same property, with the same kind of customers, it makes arrival. Okay. And for each of these queues, so let us say this is Q1, this is Q2, this is Q3 and so on. So, for each of these queue you record the time, okay, and you see the arrival. And of course, for each one of them there will be different cases. Okay. They are identically prepared, that means statistically identical, or the customers have similar kind of property, but when they will arrive, that is depending on their whim, right. So, you do that, you record for 1, for 2 and so on, and then you choose a particular time window of duration t. Now, you observe how many arrival over here in the first case. This is now called the sample, one of the sample. You take another sample, the second one, over this t again you see how many arrivals are happening, and then you go across, this is called the ensemble, go across the ensemble. At the same frozen time you go across the ensemble. Earlier we were doing at the same frozen, let us say sample, we were going across the time. So, that was time average. Over here if we do same thing and again we try to calculate the number of arrival per unit time, or which is called the lambda. If we calculate, so that will be the new lambda, which is the ensemble lambda. This is where we are interested, means this is what we are interested in. Now, what we should get is something like this. When we talk about stationarity, so we should say that the statistical property of these ensembles do not vary over time. So, it does not matter which time instance I take, is it over here or is it over here, it does not matter which time instance I take, irrespective of that time instance, you are always getting similar statistical property. One of the statistical property is this lambda, which is the average arrival rate. So, that must not vary. So, basically if this lambda t is wherever you go, so that will be irrespective of t. So, if this is T1 and this is T2, there will be all irrespective of. So, suppose this is my T2 and this is my T1, that first instance. So, wherever you start your this one, if the lambda becomes irrespective of this one and the subsequent other statistical properties also, means all the higher order moments also, this is the first order moment actually, this is the average we are taking. So, all the moments if they are not changing, or rather we should say it can be described by a distribution which is basically invariant of time. If this happens, then we call this a stationary random process. Now, you might be asking what distribution we are talking about which needs to be stationary. So, let us give little bit of hints about that, the distribution that we are talking about over here. Okay. So, what we are trying to do is something like this. So, basically whenever we have this particular things, okay. So, let us say I have some particular things which has happened. So, basically this arrival has happened, I have time equals to 0 and this is the first arrival that has happened. Okay. So, let us say at T1 I have something, then T2 I have something, T3 I have something. Okay. So, whatever is happening, now every time instance I can measure some property. Okay. Let us say my property is at any time instance. So, these are the arrival which has happened, but now I will be defining, or let us just differentiate it, maybe this is the arrival, I will be now putting some instant tau 1, some instant tau 2, where I am actually probing the system, some instance tau 3. From there I will be assigning some t amount of time, and I will be trying to see how many arrival has happened. So, this number of arrival, that count, that is the variable, okay, which is a random variable, because how many arrival will be happening at tau 1, that might be a function of tau 1. Okay. So, that is possible. So, basically let us call that I have, let us say, some tau 1 at time tau 1, I have some x 1 number of arrival, okay, at tau 2. So, basically I take this time t and I have another x 2 number of arrival and so on. Okay. So, x n some tau n number of arrival, something like that. Okay. So, these things are my random variable now. So, x 1 is a variable that is telling that at time instance where I have frozen it as tau 1, what is the number of arrival that has happened. Now, because there will be multiple such samples, so everywhere things will be varying. So, this particular value will be a random value, it can take any value, I do not know which sample I will be picking, accordingly the value will be dependent. So, it is a random things. So, every time instance you freeze, you will be getting some random value. Okay. So, that might be x 1, x 2, x n, only thing is that it is a random process, because it also depends on that time instance. Okay. At tau 1 what will be happening, at tau 2 what will be happening, how many arrivals will be happening. Okay. So, now suppose I am trying to describe, because it is random, so I need to describe a probability distribution function. So, what is that probability distribution function? So, I will be now describing a joint probability distribution function. So, which is p, let us call those random things as x 1, x 2, x n, and what I am trying to do is that this x 1, let us call it tau 1, is equal to some, let us say, k 1, x 2 tau 2 is equal to some k 2, x n tau n some k n. Okay. So, this joint distribution I am trying to evaluate. So, at a given tau 1, tau 2, tau 3 like this, I can take infinite number of time instance. So, basically my instances will be infinite. So, these infinite time instance, whatever values I will be getting, their joint distribution I am trying to calculate. Okay. It is a joint distribution at every instance, you take them and it is a joint distribution. That means that at tau 1 x 1 number is arriving. So, let us call it maybe 1 or 2, 1 arriving, at tau 2 2 arriving, at tau 3 1 arriving, something like that. This all possible joint distribution I am trying to calculate, that what is the probability that this whole event will be happening. These joint distribution we are interested in. Okay. Now, these joint distribution must be stationary. What does that means? That means even if I shift my time instance, that means these joint distribution I calculate like this, x 1, x 2, x n, at let us say x 1 tau 1 plus some amount of value I wish to put, tau equals to k 1, sorry I should not write equal to now, what I will be saying that should be making it equal to tau 2 plus tau. So, everywhere I am actually shifting this tau 1 by some amount of tau, tau 2 also I am shifting by some amount of tau. Okay. So, the time instance, their relative differences will remain the same, only thing is that the whole frame will be shifted by amount tau. So, these things, this joint distribution must be equal to the previous one for every value of tau. Okay. This must be true. Once this happens, that means the joint distribution is basically wherever you take your time, the joint distribution remains the same. Okay. So, if the joint distribution remains the same, all other lower marginal distribution will remain the same. So, therefore, if I just freeze one particular time instance, I do not take this joint distribution, only tau 1 I take, I do not have tau 1, tau 2, tau 3, tau. If I take only tau 1, that is the marginal distribution. From the joint distribution I can derive that, okay, by successively integrating. Okay. So, if I take any marginal distribution at any time instance tau 1, okay, or tau 2 or tau 3 for instance. So, there if I, that means I am freezing the whole time or concentrating the whole time into one time instance, and then I take the distribution. So, that is when you will be getting the first moment actually. Okay. That is when, as you can now see, all these time instances, it just gets concentrated over here, and that is actually we were doing for average, and we were saying that this average, irrespective of where I take, they will remain the same. Okay. So, once I do this complex joint distribution of infinite time instances possible, if that is stationary, then the subsequent all marginal distribution will remain stationary. So, therefore, first moment, second moment, autocorrelation, everything will remain stationary. Okay. So, this is the random process that we are discussing about. For arrival, when we say mathematically we are trying to give a description, this is what we are talking about. You might say practically, let us take the call arrival, right. So, that call arrival might not have this property. You might say, you might argue that call arrival probably might not have this property. I agree, probably over a day it might not be, because there are busy hours, there are let us say not so busy hours. So, let us say in a office area, if you are trying to see the call arrival. So, in the daytime it will be very busy, because everybody is in office, they are trying to use, they are trying to make calls. So, at that point probably that office area will be very busy in the morning. So, there the average amount of calls coming per unit time will be much higher than in the evening or maybe late in the night or early in the morning, right. That might happen, but over the days if you try to see in the same time instance, it will be remaining stationary. So, almost similar kind of average rate will be happening if you are not actually building up new buildings over that office area. So, as long as the other things remain same, so you will be seeing that probably the average arrival rate will remain similar. Okay. And not only average arrival rate, the other properties also will remain similar. Okay. So, if we have a corresponding stochastic process. Okay. Now, if we have understood that we can take fairly well this assumption that it is a stationary process that we are trying to describe. So, now what can we say more about this stationary process? Can we try to derive this distribution, this joint distribution, or some distribution that describes those call arrival process? Can I get that? Because if I can get that, then only I can go ahead and do some analysis. Then only we can try to say, okay, for all kind of random arrivals, I can still say what will be my blocking probability given this system design. Okay. So, to system design, that means the queue and server, they are designed. From there we want to get a relationship with respect to the input process. Okay. Whatever the input random process, we take that from the system design, can we now claim that this will be the blocking probability for this particular stationary input process. So, that will be our target. Now, let us try to see if we can say those things. So, for those things we might require some more property which are very realistic, but it is fundamentally will give us some mathematical insight. So, let us try to understand those properties. So, I will list down two properties actually that will be important for us. One is called independent increment. And second thing is called non-simultaneity principle. Okay. So, these two things I will describe them fundamentally, because once you understand these two things, you will see that very nicely that whole distribution will be derived just by assuming these two things. So, let us try to understand this independent increments and non-simultaneity principle. So, I will start with the second one because that is the easier one. So, what is this non-simultaneity principle? Non-simultaneity principle says that over here what we are trying to do, we are actually trying to account for events. So, non-simultaneity principle says in this world, this is true actually, in this world no two events, however geographically separated they might be, however distributed they might be, no two events occur simultaneously. It is almost like Pauli's exclusion principle. Okay. So, it says a very fundamental property that in time no two events can occur simultaneously. This is impossible, this will not be ever happening. Why do I say so? Is this making sense? So, we might be thinking that okay, if I make an arrival, it might be possible that I take one of my friend and we arrive together in a particular room. So, are we not simultaneously arriving? You might argue that way, but what I can say that you know that 100-meter race people used to do this photo finish, right. So, before the photo finish was there, people used to think that okay, there was probably a simultaneous arrival. That means two persons have arrived at the same time to the touch line, and probably they are should be both of them should be declared first or second, and so on. But after photo finish, people have started understanding that no, maybe if I make my time smaller and smaller, maybe a femtosecond interval if I try to observe, then we will be able to see that even between those two arrivals there are some, however small it is, there will be some differences. So, basically if you go into the minuscules of this time intervals to femtosecond to nanosecond to so on, you will always see there will be difference between two arrivals. Okay. So, that is the basic fundamental property that nothing, no two events in this world can happen simultaneously. So, that is the non-simultaneity principle. Okay. We will see the mathematical description of that in the next class. And then the other thing is called the independent increments. This is also a very fundamental property of this kind of arrival. They will be classified as a special kind of arrival. This is something we are enforcing. This is not like non-simultaneity principle that always happens. This is something we will be enforcing, and this is something we will be calling as Markovian property or memoryless property. So, it is called Markovian or memoryless property. Okay. Markovian came because of the person who has innovated these things. So, Markov, his name, from his name, and it is memoryless. You will later on see that this is something called where the history is erased. These processes are special process where the history means the future events. So, suppose I am staying at this, all the future events if I try to predict, because these are all probabilistic events. So, I can always try to predict from here, I can try to assess or guess that what is the probability that this will be happening. So, that I can always do. So, when I am trying to predict my entire history about what has happened previously, if this has some influence in my prediction, then that is called memory process. But if it does not have any influence, that means only by seeing the present I will be able to predict what will be happening in future, and I do not have to know what has happened in the past. So, if it is not dependent on past events or past occurrence, then this is called memoryless, and the corresponding associated property will be independent increments or independent increments or independent, if we define independent intervals, then we will see this independent increments. What does that means? That in a time event, if we can define two independent or non-overlapping intervals, then we can again say, this is the actually very generalized principle of that whatever is happening over here has nothing to do or no dependency over whatever is happening over here and vice versa. So, that is called the independent increments. Okay. So, these two things will mathematically define in more detailed way in the next class. Okay. Thank you.